All right. Please welcome Andy.
Thanks, Natalie. Welcome, everyone. My name is Andy Gooding. I'm the VP of Engineering at Aerospike. Aerospike, as many of you probably already know, or hopefully know, we make a NoSQL database. Why another database? Our specialty is extreme performance at extreme scale. So extreme performance meaning very, very high throughput, very low latency, and extreme scale meaning terabytes, even petabytes of data, and hundreds of billions of records. So I've been there for 8 years, which is almost to the very beginning. And way back then, Aerospike was what we call a high availability database, which we'll address in the talk. But a couple of years ago, we began to realize that this high availability mode is not really acceptable for some use cases. And we decided that it was time to add the other mode, strong consistency. We tried a very novel approach to strong consistency, which seems to have worked out really well. And we'll get into a little bit about what's novel about it. But the talk really is not primarily about Aerospike's strong consistency. It's just a talk about strong consistency in general, what the trade-offs are with high availability, what it really means, what your concerns might be choosing between the two, and in general, what it guarantees. So I gave this talk last year in Israel, and I was literally not allowed to mention Aerospike during the talk. So you'll see it really is a very general talk. Although at some points I will mention Aerospike's implementation just to highlight the fact that you don't necessarily have to do things one way or the same way to achieve strong consistency. So again, the talk's really just about strong consistency in general and the trade-offs compared to the alternatives. Okay, good place to start is the CAP theorem, which if you have not heard of this, it is a theorem that states there are three things in a distributed system database: strong consistency, which the subject of this talk mostly, maximum availability, which we'll also talk about a bit, and toleration of cluster partitioning. And the theorem, which I'm not going to prove here, but as the talk goes on, you'll kind of get the idea why this theorem is true. The theorem says that you can only get two of these three. You can't have all three. And again, as the talk goes on, it will sort of emerge why that's true. So I'm not going to bother prove it here. You can look that up if you really want to see it. So yeah, you can only choose two of these. And of course, in the real world, one of the two you're going to be choosing is P. Meaning that this really is going to boil down to a choice between which you're choosing between C and A. So why do we choose P? Or why do we have to choose P? And the reality is that cluster partitions in real distributed systems do happen. You're going to see nodes crash, and you're going to see connections in your network break. And the reality is that even if you have a really, really good system, someday, somehow, this is going to happen, and you're going to end up, it may be important whether you decided to choose C or A in this scenario. So let's see, some other terminology I might introduce in case I start spewing slang through this talk, when connections break, you might often hear me talk about a split or a split brain. That's a scenario where the user application via a client can only see pieces of the cluster, but they can't see each other. Sometimes also the clients won't be able to see certain pieces of the cluster, but that's what we mean when we say cluster splits or split brains. When nodes split off, if they're completely disconnected by network, it's more or less the same as if they did go down. They're no good to anybody if the application can't see them and if other nodes can't see them. But sometimes nodes just literally will go down too, much as we'd like to think we can write perfect software. Some other things to clarify about our choice between strong consistency and maximum availability. Strong consistency does have a very clear definition, which I will explain shortly. And maximum availability, I've heard different definitions of it. My definition is pretty much if you can see any part of the cluster, any node, then transactions are allowed to proceed. Now note that maximum availability doesn't mean 100% availability. Even if you decide I'm going to choose A and I'm going to have a highly available system, if all your nodes go down, I can tell you that your availability will actually go to 0, even though you've chosen A. So maximum availability just means that pretty much you're going to take any availability that you can get. Meaning, if any node is visible, we'll let transactions through. Also, want to point out that just because you're making this choice, it doesn't mean that every situation in which you have a cluster partition will cause you to give up the other thing that you're choosing not to have. So choosing strong consistency does not mean that every situation causes you to decrease to be less than maximum availability. And likewise, choosing a highly available system doesn't mean that every partition scenario necessarily breaks strong consistency. So a good distributed system, for example, should at least allow you to upgrade where you don't lose either C or A. Meaning you should at least be able to take a node or perhaps more nodes down in sequence to upgrade your software without any loss of availability or consistency. And that's for us, when we were developing our SC mode, that was pretty much the primary criteria, is that we have to make it so that our availability loss is 0 during what we call normal upgrade scenarios. So yeah, it's not always that the first thing that happens, any node going down means that you're going to lose one or the other of A or C, depending on which one you chose. Okay, so I said I was going to define strong consistency. So my definition, which I think is pretty well agreed on in general, is that what you must see in the cluster is a single linear progression of a record version. By the way, for this whole talk, I'm really talking about single record transactions. If I ever say anything about a record or a transaction, we're not talking about multi-record transactions here, but this whole discussion applies just fine to single record transactions. So what we mean here is, as we do a series of operations, write operations, we'll only see one sequence of version emerge, of a record version emerge. The corollary is that any successful operation has to be reflected in the progression and never be lost. So once you've done something to affect a record and the database told you that operation succeeded, you can't ever after that encounter a version of the record where it was as if that operation didn't happen. So to me, this is really the primary definition of strong consistency. We guarantee that you will never lose a write. Notice also that our operations here, they don't necessarily have to be literally an atomic transaction, an operation in an atomic transaction. It could be a read, modify, write, which is two transactions where, you know, the write is optimistically reporting the generation that it read and will fail if it's not encountering the generation that it read. So the operations can be a read-write combination, or they can be an atomic thing where it's just one transaction that takes the existing version of the record and based on that generates the next version of the record. Now, my definition is all about writes, which of course involve looking or reading the previous version of the record. I'll defer talk about read-only version progressions later. I don't want to, we'll talk about this definition a little bit again then, but for now I want to keep clear that when I'm talking about strong consistency, essentially my view of it is I'm not losing writes. Okay, so what's high availability then? High availability means that operations, as I said earlier, will succeed as long as any part of the cluster is visible. So I'll take the operation and I'll do it. It doesn't matter even if the situation is that I can only see one node and it can't see any of the other nodes. I might still decide that, yep, I'm going to let you go ahead and do a transaction. What it means is that you're going to violate that linear progression that we defined, that single linear progression that we defined was the basis of strong consistency. So the record progression can now split, which will break strong consistency. So to redraw our original sequence where we had operations 01 through 04 starting at version 0, if operations 01 and 04 happen in one split of the cluster and operations 02 and 03 happen in another split of the cluster, then you end up with these versions which are absolutely none of them will be the same. Well, maybe VA will be the same as the first one that you saw in the strongly consistent sequence, but in general here, you're going to end up with scenarios where you have different versions of the record in the cluster, which you can see, and the versions are not the same as what you would have if there was strong consistency. In other words, you'll be missing writes. VY will be missing writes 01 and 04, and VB will be missing writes 02 and 03. And this is irrevocably breaking strong consistency. It does not matter if somehow we magically are able to recover V4 as it would have been if this whole situation never happened. So some people will call the scenario where we actually do recover V4 eventual consistency. And I'm going to put my rainbow-powered unicorn up here, not because I don't believe that eventual consistency is a real thing, but there is a lot of mythology surrounding it. And we're actually, it's probably good for us to spend a few slides talking about what this really is. So the first big myth that I see around it is this conception that it's somehow a step along the way to strong consistency. So I've had discussions with customers that sound like the following. The customer will say, well, for this particular use case, we'd like strong consistency, but we can make do with eventual consistency. So it's okay if you can't deliver strong consistency, we'll settle for eventual consistency. And I'll ask them, wait, do you prefer eventual consistency, meaning the increased availability in these scenarios, or do you prefer strong consistency? And they repeat, well, I prefer strong consistency, but we can we can manage without it. It's okay if you just give us eventual consistency. And the myth there is the word just. It's in their mind, maybe it's a stepping stone on the way to strong consistency. But in terms of implementation and what it entails, it is absolutely not a stepping stone to strong consistency. They're very different things in principle, and they take very different techniques of implementation to accomplish. And eventual consistency is actually every bit as difficult, in arguably more difficult to do than strong consistency. The other thing about eventual consistency is it's often slung around as a general term, as if I really can always easily just recover V4 without any data loss, or without, again, as if nothing in between happened. But in reality, most practical implementations of eventual consistency are incredibly use case specific. It turns out to be really hard to do it generally. So let's talk about why. Even in very simple cases, you'll see that to do eventual consistency is going to have some extra cost. For example, I'm showing a situation here where our operations are just arithmetic addition. So you're just incrementing some number. The value of the record is just a number. And you can see here that just knowing the end states of two splits, like VB and VY, is not really enough information to recover what the record should have been if none of this happened, the V4. You can't tell from those values, 111 and 112, that when you merge them together, the value is supposed to be 123. So you have to know, in this scenario, at least have to know what the value was when the split happened. And remember that, this is a simple splits. There could be many splits, cross merges between splits before you have a final merge. You can have splits where there's no version of the record to begin with that you have to merge back. So it can get pretty involved. And in general, to do even this case, you have to know what the versions and values are at the splits. Alternatively, of course, you also have to know when you're split, or you literally have to store all the versions and values. And even things like knowing when you split, in other words, when you can trim your history to start from scratch, is a pretty involved thing. So even a simple case like this, you're going to end up dealing with history, essentially. You're going to end up dealing with state and history to be able to recover the version of the record that you want. And if you are really trying to do things in general, it gets even worse, because in general, you can't derive operations from values, even if you know what the original value was and what the final value was. You don't really know what operation got you there. And conversely, just because you know what the operation was and the final value, you can't actually derive the original value. And notice in this case, I put a hash there as an example, but many things do this, like mods, just trimming, selecting. You can do there any number of things that essentially lose you information irrevocably. So it can be even worse when operations don't commute, because even if you know the operations and you know the values, it depends what order they were applied in. And again, here I've done this with arithmetic to show you that two things that aren't switchable, but it's a lot more common than you think. Even simple things like concatenation. If I start with a string cat and I append woman and then rules, it's very different, whether you get cat woman rules and cat rules woman. So you're gonna see this problem in a lot of use cases. So what all of that means is that it isn't even enough to know the versions and values at the split. You have to know in general, you would have to know all the operations and the order in which they were applied in between and all the splits. So that's a lot of cost to store all of that. to keep all that state and information and history to be able to accurately recover the version that would have been if the splits never happened at all. And maybe for some databases that actually might not be a big ordeal if they're already storing multiple versions of records and histories and accurate transaction IDs or operations logs. If they're already doing that for other reasons, then maybe this is actually not that much of an extra chore. But for some databases, like ours at Aerospike, we only store one version of the record, the latest version, and we don't have an operation log. And so for us, this would actually be very, very difficult to do. It would be very costly and very different. You'll often hear the words CRDTs slung around, like, well, why don't you just use CRDTs or user merges? But those are really just names that package everything I just said. A CRDT will be a way of storing the necessary history and information to do resolution for a particular use case. CRDTs in general are also, well, again, because they're eventual consistency, they necessarily are, notice that they're not, don't let anyone kid you, they're not giving you strong consistency. And also don't let anyone kid you, they are always very use case dependent. So when you're going to use a CRDT, it'll definitely be a CRDT that caters to a certain kind of operation or a use case where it can recover things in a limited fashion only for that use case. Some CRDTs will even actually lose data on the merge, and that doesn't even give you the so-called eventual consistency. It's just a controlled or stated way of how you want to lose your information, how you want to lose your writes. And in general, they're also very complex things, and for a high throughput, low latency, a large scale database like Aerospike, something like this would be a big challenge. So in general, eventual consistency for a lot of databases is going to be a pretty extravagant cost. So when we were faced with a choice, we actually chose to do strong consistency first, or so far it's really the only one we have, because strong consistency, unlike eventual consistency, is actually very use case independent. It doesn't really matter what your use case is, you're going to get your guarantee. It has its own challenges, of course, which we will now get into, but I just wanted to clarify that eventual consistency is absolutely not strong consistency. They're very different things, and they take very different strategies and implementation. Okay, so again, to recap, if you're choosing a high availability database, it'll generally mean that when we resolve your conflicts in these split brain scenarios, what will happen is you're going to lose a write. You're going to lose something. So in Aerospike, for example, we allow you a choice of two very simple schemes of merging records back from splits. One is that you'll just pick the latest. The other is that you'll pick the one with the most history, which, by the way, a lot of ad tech, a lot of our customers in general choose this option because usually if you're merging two things back and one of them is the entire history of the record that was there and the other one is just this spurious new little stub of a record that was created in some branch and it happened to be later, you don't want to wipe out the bulk of your information. So they would rather lose the later single write or very few writes than the slightly earlier but containing much more information record. By the way, notice also to go back to this slide where we pick the latest. Sorry, I guess I have to go two back. Yeah, where we pick the latest. If my usage model happens to be that every operation simply replaces the record and doesn't depend on the previous value, well, hey, this scheme gives you eventual consistency because this is exactly what you would have seen if the split didn't happen and these things happened in this sequence. So I'm just saying that to point out that the ultimate use case dependence of eventual consistency. So yeah, we do eventual consistency for the use case where you just replace records and don't care about the previous value, which admittedly is not that common a use case. Okay, so if you choose A, what it means is that there are going to be scenarios eventually someday where your record progression will split, and it'll be observable in this split. In other words, you're going to be allowed to do writes and reads on the split values, and by definition, you've broken my definition of strong consistency, that single linear sequence. And at the end, you're going to end up doing conflict resolution of your split lineages, and either it's going to be very complicated and require storing lots of history to get back the best version that you possibly could, or it's going to be something much simpler and cheaper and that will result in data loss, or both. So there's your high availability. And again, we at Aerospike had only this mode for years, and we did quite well. For a lot of use cases, this is what people want. They don't really care if they occasionally lose a little bit of data. They invest their efforts instead in just trying to make sure that the scenarios in which this happens are minimized, get the best network you can, manage the cluster the best you can, and hope that Aerospike writes good code so that their nodes don't crash all the time. And it, for many customers, has worked fine. They can run for months or years, and they don't really get any of these scenarios, and they don't lose any data. But again, someday when the scenario happens, for some use cases, it's just not going to be acceptable. Okay, choosing strong consistency. What does that mean? The strategy in general is to disallow operations that would cause record version splits. So for example, here in the picture, as you see it, if I can only see a piece of the cluster and I know that this is going to cause a version split, I'm just going to not allow you to do the operation. The other thing is you have to disallow observations of dirty versions that somehow do get there when they would cause a split. And just a word on that. In general, it's pretty hard to avoid getting dirty versions, what we call a dirty version in any system, because in general, you can commit a write on a node at a time when everything is fine, but before you can finish the whole transaction and all the replicas of on the nodes that they need to go on, then something goes wrong, and you actually end up at least temporarily with this version which is dirty. So the corollary of disallowing operations that would cause record version splits is if something does somehow get in there that would cause that, you have to disallow observation of those versions. So you have to know when they're dirty and pretty much not let them participate in the database activities. So that is pretty clear that if we're going to be disallowing operations on nodes which you can see from an application, by definition I'm violating my maximum availability premise. So there's where strong consistency is going to give up availability, because we're literally going to stop you from doing transactions that will cause splits, even when we can see a node that we would otherwise, in a high availability scenario, done a transaction on. Okay, I said at the beginning when we gave the definition of strong consistency that there were choices of read-only behavior. So what do I mean by that? We've established that for sure we're going to have a single linear progression of the record version. And our first mode that I'm going to talk about, which we call session consistency for reads, means that a given client, a given view of the cluster will never see a stale version, meaning that, you know, if it did a write, if it did write 04 and created version v4, it can't do a read that would then see version v3. Now there's a stronger version of read sequencing, which we'll call linearized reads, which means that even across different clients, we can never see a stale version, meaning that even if client A wrote operation 4 and created version 4, if client B reads that record after that, it has to see version 4. It can't see version 3. In session consistency, it might be possible for client A to write version 4, but client B then goes and reads and finds version 3 because its map hasn't caught up, or whatever the implementation detail is. So while the single client will see a linear sequence and never go back, if you actually had a way for A and B to compare notes, you would find that one managed to do a write and the other one after that write didn't see the write. Now a lot of people ask, before I get to the difference between those, there's a third version which we in Aerospike support, which is what we call relaxed, where it's perfectly fine to see stale versions even in a single client. The main care is that writes are never lost. They don't really mind if occasionally you see a stale version in the single history. But yeah, one of the most common questions we get asked is, well, should we use the linearized mode, which, as it turns out, has a pretty high performance cost as compared to session mode? And the best answer I can give is, if your clients actually do have a way to compare notes with each other, then maybe you want to think about it, if they have a way to compare outside of Aerospike. But if there is no source of, or no way for them to compare notes, or no source of truth outside of Aerospike to verify that they were in sequence, then pretty much that means that then you don't really need the linearized mode, because if you can't know about what the other client saw, then it really only matters what one client sees, and then you can go with session consistency, which, by the way, is does seem to be the mode of choice for many of our customers. Okay, so yeah, again, none of this changes what we said earlier about not losing writes. We still have this single history. If you're doing a read as part of a write, you know, that obviously has to be in the succession of the writes, but these are read-only ordering concerns, and that's what these modes are all about. There are purists, by the way, who will tell you that if you're not doing linearized reads, you're not really doing strong consistency, and we could argue about that, but occasionally you will look that up and you'll see that that's included in the definition of strong consistency, but for me it's not. To me it's about losing writes. Okay. A traditional consensus system, so I'll talk a little bit here about traditional strong consistency implementation versus ours. Again, mainly to highlight that you can do this different ways and get the same guarantee. So to quickly run through it, a traditional consensus system, you'll have stationary versions, what I call stationary versions of a given record in a cluster. In other words, you'll always have certain nodes designated to be the nodes on which a given record sits. And when you do an operation, the operation is done in parallel generally to all those records. So your operation there went straight from your client to these nodes. By some means, it doesn't have to go straight from the client, which, as you'll see in some implementations, can provide an advantage. But the idea is that you write all three independently. and you probably have a two-stage system to verify that they all got written. And a successful operation must have written to a majority of the replicas, which actually has a corollary, meaning that for you to have 100% availability with n nodes missing, you need to have 2n+1 replicas. So here, for me to run with a node down with one of those three versions missing, obviously to get a majority, I need 2 of 3. So I'm going to need at least 3 replicas to be able to run with one node down. If I had 2 replicas and 1 node was down, I wouldn't have a majority anymore. So we have that constraint. It also means another corollary is that you need then at least 3 replicas to be able to do rolling upgrades with 100% availability, because the best you can do is take 1 node down at a time. That's the fewest nodes that you can take out at a time, and so if you want to keep your availability, you're going to need a minimum replication factor of 3. Now, one good thing about most consensus systems is they preserve partial availability really well by making use of all connectivity. Good implementations of this, you can chop out all of those, a lot of those connections, and as long as there's any path from your client that can get to the 3 or the however many replicas that sit on different nodes, as long as there's any path to get there, then you can succeed. So you can actually withstand a lot of connectivity breakages. Okay, so now I'll briefly describe the way we do it in Aerospike, just to highlight some differences. And yeah, here Kevin's system means Aerospike because in the original talk I was not allowed to mention the name Aerospike, and Kevin's one of our engineers who played a major role in designing this system. But in an Aerospike system, we'll only keep 2 replicas as compared to 3 in the other case. And the way that our operations go, it's master-centric. The operation will go first to the master, and then it will be replicated to whatever you want to call it. We call them proles, slaves, replicas. Then it'll be replicated to the other node. So they're not independent. It definitely goes in this order. And just like in the traditional consensus systems, we do have a requirement that a successful operation must have written to replication factor replicas. But in this case, notice here, all we're saying is it's just that many replicas. It doesn't actually matter what nodes they're on. And in our case, we don't necessarily always have both the replicas on the same 2 nodes. If the cluster changes, other nodes will fill in to stand in as replicas or masters, and then we'll end up being able to complete a transaction as long as we can get to enough of the nodes. So what that means for us is that we can have 100% availability. One corollary is with only n nodes missing, if we have n+1 replicas. So that means, for example, that we only need 2 replicas to be able to do a rolling upgrade with 100% availability. So that turns out to be quite a big advantage, obviously, for cost, if you really only need to carry 2 replicas instead of 3 to be able to keep your 100% availability. And on the downside, what we find is while we maintain 100% availability perfectly well in these cases with fewer replicas and in very simple splits, our partial availability as compared to a traditional system will decrease quicker as connectivity worsens. So we can actually get scenarios where, you know, if you chop out enough connections, we'll actually go all the way to 0 availability, where a traditional consensus system might retain quite a bit. So there are some trade-offs, but we think they're good. Okay, the trade-offs, again, just to summarize, is that in Aerospike, we need fewer replicas to tolerate a given number of nodes down and maintaining 100% availability. Or we can, the opposite, we can tolerate more nodes down for a given replication factor. So I could have replication factor 3, I can actually take 2 nodes down at a time and maintain 100% availability, whereas it would be 1 for a traditional consensus system. So for a given tolerance, whichever way you want to do it, it just means that you're going to end up with lower costs because you're carrying fewer replicas, and higher performance, again, because you're carrying fewer replicas, so there's just less work to do a write. There's just less going on in the system. Traditional system advantages, as we said twice before, is that they're generally much better at preserving partial availability in more severe cluster partitioning scenarios. Okay, getting near the end now, the final recap. The choice of C versus A really is about what do you prefer during a very rainy day cluster partitioning scenario. And remember, it has to be very rainy. If it's light rain, just meaning like I take nodes down on purpose to do an upgrade, or one node goes down by accident, most systems will give you both for free. We certainly do. So it has to get a little uglier than that before the choice between C and A manifests itself. So guaranteeing C, if that's the choice you make, you're going to sacrifice A on really rainy days. It may be more involved to deploy. For example, our strong consistency system, you have to manage a roster. The cluster has to actually know what nodes are supposed to be in it, where our high availability mode, you know, everything is very free about that. The cluster just develops in terms of what nodes can see what nodes, and you don't have to specify anything. So there is a little bit more operational play involved. Sometimes it can cost more or hurt performance. In Aerospike's system, it has almost no cost. In fact, for replication factor 2, it pretty much does have no cost. But in a lot of other systems, it is going to cost you more, if for no other reason, by making you carry more replicas and do more work per write. But it doesn't have to. I mean, we do a pretty good job of that. And high availability systems, which sacrifice strong consistency on very rainy days. Again, notes to remember, eventual consistency is a complicated thing. It can actually cost you more than strong consistency in terms of complexity or performance. But otherwise, you know, if you keep it simple, then your high availability system is going to lose data on your very rainy days. So that's the choice you're making. And that's pretty much it. This is our optional slide. If you guys want to hear about this, we can address it in the question session. But for the talk in Israel, people wanted to hear about this. There are these tests done by Kyle Kingsbury, who's an independent contractor that goes around and tries to ensure or debunk your claims about whether your database is strongly consistent. He came to us and tested everything we claimed, and we passed the test, which is not a trivial thing to do. So if you're really considering using strong consistency, you should probably go and read that, and at least be happy in the fact that that a third party is telling you that our claims seem to be true and that this isn't just salesmanship. But if anybody has any questions and details about that, you know, feel free. We can talk about it afterwards. And that's it. Thank you very much. Now I'm going to see how long I took.
Thank you very much, Andy, for the talk.
Okay.
There are no questions in the chat, but I'm changing the settings so that anybody who would like to ask a question is now able to unmute themselves and present a question. So please go ahead. If you want Andy to create the more flesh, maybe you can bring back that slide.
Is anything happening, Natalie? I can't.
Nothing is happening. So maybe you can bring back the slide that you just mentioned and discuss about that a little more.
Well, we can talk about any slide.
The one that you mentioned, you're thinking to add more details depending on how the questions go. So maybe we can.
Well, I mean, if people want to ask specifically about what the Jepsen test is and what it does and our experience with it, I'm happy to talk about it. But I'm happy to talk about anything else too.
All right. First question actually came in the chat. What does strong eventual consistency mean? It's a term I heard related to CRDT.
Yeah, so I don't really understand why they put the term strong on eventual consistency. What I described as eventual consistency, I think, is what they mean. Actually, I think they may mean even less, because if it's who I think it is an eventual consistency for particular use cases as done by a CRDT, but I believe these CRDTs also will actually force you to make a choice as to how you lose data in certain merges. So to me, that doesn't even qualify as eventual consistency. But I don't know what the intent is to add the word strong to eventual consistency. You're either eventually consistent or you're strongly consistent, and I don't know that there's an official definition for a strong eventual consistency. The strongest it can be is to go back to, if I can find the slide, the strongest, no, it's further back. So yes, here, the strongest it can be is that in general, anything that happens here when the merge happens and the smoke clears and the cluster reforms itself, you end up with exactly the version that you would have had if none of this cluster split situation happens. And that's as good as you can do in terms of eventual consistency. So there's nothing stronger than that. And achieving that in general is unbelievably hard. If you have CRDTs, almost certainly the CRDT is specifying a certain use case or usage model. Like it might be saying if you're doing numerical increments or whatever else that it covers. And in those cases, it might be good enough to actually do this, which is what I would think I would call strong eventual consistency if I was going to put the word strong. Or it might actually cause you to make merge choices where you do lose rights, in which case I don't even understand why you're calling it eventual consistency. It should just be, eventual conflict resolution, because if you've lost anything, you're not really consistent. So yeah, I don't, the answer is I'm not really sure what they mean by that, but I'm guessing there's really no distinction between that and what I described in general.
Thank you. Are there more questions? You're welcome to ask about the talk. You're welcome to ask about Aerospike.
Yes, anything goes.
Well then, the sketch note is actually being already shared and ready, so that's great. Thank you for sharing it, Miriam. And looks like we're coming to the end of our event. So if you want to ask questions afterwards, you're always welcome to join our forum or Reddit. Easy to Google, and we will be there to answer questions. Thank you very much for coming. Thank you very much again, Andy, for this talk. And
you're most welcome, everyone.
See you all in the May event. And this talk will be uploaded to our YouTube channel.